Anybody who watches the sky with a fraction of the attention that ancient people did will notice a couple of things right away. The sun maintains a constant size and brightness and moves at a constant rate across the sky all day long. In the evening, it approaches the horizon, reaches it, and proceeds fully below it, creating night shortly thereafter. Ancient cosmologies generally were based on a flat Earth, but they all knew that the sun had to set to create night. And when it set, it was night everywhere. But thousands of years ago, it became clear that the sun didn't set for everybody at the same time, and it gradually became clear that it was always day somewhere, a thing that was simply impossible given a flat Earth. Call it the time zone problem. On a flat Earth with a distant sun, if it's 3 o'clock in the afternoon somewhere, it's 3 o'clock in the afternoon everywhere. If it's sunset somewhere, it's sunset everywhere. If it's night somewhere, it's night everywhere. And of course, the only way that can happen is if the sun is on the other side of the flat Earth. Undaunted, in the early 1800s, Samuel Rowbotham proposed a model in which a local sun circled around always above a flat Earth, making daytime in those places that it was close to and night further away. And while it should be immediately obvious that a sun like this would change its size over the course of a day, violating direct observation, the model took hold. The larger problem, of course, is that a sun that's always in the sky can't set, and a sun that doesn't set can't make night. Nevertheless, let's work out the details of what this might look like. In what follows, I make these assumptions. 1. The Earth is flat. 2. The sun is at a constant altitude. Flat earthers will typically quote numbers like 3,000 to 4,000 miles. So I've used 3,000 miles in what follows, though that choice is largely irrelevant and has no bearing on the appearance. 3, the sun moves at a constant velocity. This is a simplification from the circular path that it might follow on a typical flat Earth model, but it does ensure that the sun moves away from the observer, hastening nightfall, which, as we'll see, nevertheless never comes. 4, the sun passes directly overhead at noon. 5, the sun appears at its actual apparent size when it's overhead, and because the sun is in fact always half a degree in angular size, this assumption translates to a solar diameter of about 30 miles, because an object 3,000 miles away would have to be 30 miles in diameter to have that angular size. And finally, that the sun moves to a position 30 degrees above the horizon at 4 p.m., mirroring something like what we typically see. As shown in the second diagram, when the sun is at an elevation angle of 30 degrees, its distance from the observer will be twice as great, 6,000 miles. Although I don't show it on the diagram, that sun will have moved about 5,200 miles horizontally during that 4-hour period. In subsequent slides, I simply move it by that same distance, generating the positions at 8 p.m. and then midnight, from which we can calculate that the observed angles above the horizon at those times will be 16.1 degrees at 8 p.m. and 10.9 degrees at midnight. And yes, you heard that right. At midnight, the sun will be 10.9 degrees above the horizon. I've also placed in these diagrams the apparent size of the sun at each of these times based purely on its distance. When the sun is twice as far away at 4 p.m. as it was at noon, it will appear half as big. At 8 p.m. it will appear 28%, and at midnight it will appear 19% of its size at noon. These two should be understood to be in conflict with what's actually observed, because the sun does not vary by even 0.1% over the entire course of one day. In what follows, I show a sequence of drawings of what the sun will look like at 4-hour intervals. The first picture at 4 p.m. shows a sun 30 degrees above the horizon and half the size that we see it when it's overhead, which is indeed half the size that we ever see it in reality. Note that in all of these pictures, the angular distance between the horizon and the sun should be about 100 times the diameter of the sun. Nevertheless, for visualization's sake, I've consistently drawn the sun itself about 12 times larger than it would actually appear. So let's follow the sequence, beginning at 4 p.m., moving to 8 p.m. when the sun is about 16 degrees above the horizon and getting smaller. At midnight, when it's some 10 or 11 degrees above the horizon, getting smaller yet. To reiterate, this is at midnight. Moving on to one full day afternoon as the sun continues to get smaller and closer to the horizon. And moving on to 2 days afternoon when the sun has reached within a few degrees of the horizon for the very first time. And finally on to 3 days after noon when the sun is now something like 2 degrees above the horizon. It's worth noting that the sun is now nearly 100,000 miles away, much larger than the diameter of any proposed flat Earth. And at this point, it has just become, for the very first time, an unresolvable point of light to the human eye. Because it is now nearly 30 times as far away as it was at noon, it'll be 1,000 times less bright, and that leaves it 500 times as bright as the full moon. And of course, it is still nearly 2 degrees above the horizon. So just to recap that, the sun, 3 days after passing overhead, has for the first time become unresolvable as a circle, but is still the brightest thing in the sky by a factor of at least 500 and is still 2 degrees above the horizon. The final slide puts all of these together and illustrates what will be obvious to anybody that understands perspective, that an object moving away from us at constant altitude will appear to approach a vanishing point at the horizon, never reaching it, and always getting smaller and smaller. So I end by playing through the sequences of what evening looks like on a flat Earth, and what evening looks like on the Earth. Judge for yourself.